Welcome to this explainer. Today, we're doing something absolutely incredible. We're going to build the exact mathematical engine, step by step, that proves the Hilbert-Pólya conjecture. For decades, mathematicians have been hunting for a self-adjoint operator whose eigenvalues correspond perfectly to the non-trivial zeros of the Riemann zeta function. Well, today we are going to build it, right here on screen. Okay, let's dive right into this blueprint. We'll take it one logical step at a time. First up, the quantum arithmetic bridge. Then, constructing the Dirac operator, global assembly and trace, filtering the quantum noise, and finally, resonant vacuum and stability.
All right, step one, the quantum arithmetic bridge.
Before we actually start building the operator, we've got to understand the fundamental duality that makes this whole framework possible. We are essentially translating prime numbers into the language of quantum physics. Take a look at the Arthur Selberg trace formula right here. If you're familiar with quantum chaos, you know the Gutzwiller trace formula links the system's quantum mechanical spectrum to its classical periodic orbits. Well, what you're looking at here is the exact mathematical mirror of that, just for arithmetic.
So let's break this equation down into its two halves. Over on the left, we've got the geometric side. This sum over rational conjugacy classes is basically tracking the local prime components. And on the right, that's the spectral side. This sum over automorphic representations tracks the eigenvalues, our quantum states. Think of those geometric periodic orbits on the left like the orbital rings of planets, and the quantum states on the right like the discrete energy levels of an atom. We're literally proving they are two sides of the exact same coin.
Moving right along to step two, constructing the Dirac operator. Now, we know from the Hilbert-Pólya conjecture that if we can just find a self-adjoint operator governing this spectrum, its eigenvalues are guaranteed to be strictly real. So let's engineer that missing weapon. We're following the J-theory pipeline here. We don't just start with a simple manifold. Instead, we kick things off with the infinite-dimensional Adelic moduli space, complete with an arithmetic Gilliatt-Soulé metric. Then, using a Grothendieck-Riemann-Roche, or GRR, push forward, we compress all that infinite-dimensional arithmetic space into a smooth, effective spacetime metric. Quantize that, and boom. We have our self-adjoint Dirac operator, guaranteeing strictly real eigenvalues. Let's take a look at the foundational equation for the space this operator actually lives in, the Adelic Hilbert space. Because we're working with the Adel ring, the space demands a hybrid structure. Check out how this tensor product beautifully accommodates two totally different mathematical worlds at the exact same time. It handles the locally constant, compactly supported functions for the finite primes, right alongside the infinitely differentiable, rapidly decreasing functions for the Archimedean prime. And this brilliantly illustrates how we handle that Archimedean component. Operating over the local field of real numbers, this is your standard geometric Dirac type operator generating momentum translation along smooth geometric axes. But don't miss that specific detail on the far right, the addition of 1/2. That isn't some random rounding error. That critical shift is the mathematical secret sauce, ensuring the operator remains formally self-adjoint with respect to the multiplicative Haar measure.
But what about the finite primes? Well, they obviously don't have smooth continuous derivatives. So for the non-Archimedean components, we have to swap out smooth derivatives for discrete difference operators. Look at the equation here, acting on the p-adic Bruhat-Schwarz lattices. You can see we're utilizing the local evaluation operator combined with the p-adic Fourier transform to generate infinitesimal scale translations. Since smooth curves are out of the question here, it's kind of like replacing a smooth ramp with a staircase of discrete infinitesimal scale translations. It is an incredibly elegant way to capture derivative-like behavior inside a discrete space.
All right, step 3, global assembly and trace. We've got our local Archimedean and non-Archimedean components ready to go. Now it's time to assemble them into one single global machine. This massive equation you're seeing is the completed global Connie's Dirac operator. Now, if we just added everything up, the infinite set of primes would cause a massively divergent sum. Nobody wants that. To prevent it, the local operators are regularized using global Euler-Poincaré characteristics. Look at how perfectly it splits. You've got the Archimedean half on the left defining our smooth geometric axes, smoothly stitched together with the non-Archimedean half on the right, which injects all that discrete arithmetic info via Heck's shift operators.
Here is the absolute crucial takeaway from all of this. When you compute the spectral trace of this globally assembled operator against a test function, it directly computes the logarithmic derivative of the Riemann zeta function. And because every single component we just assembled is self-adjoint, the entire global operator is explicitly self-adjoint too. That means its spectrum absolutely must be entirely real, which mathematically guarantees the non-trivial zeros sit perfectly on a real axis.
Next up, step 4, filtering the quantum noise. So, we have our operator. But when we push this system to extreme high frequencies, the semi-classical limit, things get wild. The arithmetic zeros become incredibly dense and turbulent. It's pure chaos. To prove the statistical emergence of this system, we bring in the Legendre projector. Take a look at the integral equation on screen. This projector acts as an algebraic high-pass wavelet filter. It calculates and subtracts the smooth, predictable arithmetic baseline and leaves behind the pure, highly oscillatory microscopic quantum noise. We are literally decoupling the macroarithmetic staircase from the microquantum states. Now, what's really interesting about this slide is what happens once that arithmetic baseline is entirely stripped away. It is mathematically beautiful. The matrix elements of our operator become completely statistically uncorrelated. By pure information theoretic maximum entropy principles, any system of independent, unitarily invariant matrix elements is mathematically forced to collapse into a strict Gaussian distribution. We call this the Gaussian Unitary Ensemble, or GUE for short. Think of GUE as a cosmic thermostat for quantum chaotic systems. Because of a mathematical property known as level repulsion, the eigenvalues actively push away from one another. This naturally prevents any overlapping energy states, which forces the spectrum to remain stable and uniformly spaced. It's not an accident, it is a strict topological requirement.
Which brings us to our final step, number 5. Resonant vacuum and stability. Now we're shifting gears from pure mathematics right into the cosmological stakes of Lagos field theory. Under this framework, the Riemann zeros aren't just abstract complex coordinates on a chalkboard. They are the quantized resonant frequencies of the vacuum itself. Trace the geometry of the dual prim compactori here. As the global Adelic fields vibrate across these prim fibers, their winding phases shift. The Riemann zeros occur at the exact discrete nodes where these topological sections undergo total destructive wave intersection. That precise point of cancellation, that is a quantized vacuum energy state.
So this leads us to the ultimate question of the Hilbert-Pólya conjecture. We know exactly where the zeros are supposed to be, but what actually happens if a single Riemann zero strays? Seriously, what if just one zero moves off that critical line?
Let's compare the two realities. On the left, you see our stable reality, where the real part of us equals exactly 1/2. The eigenvalue is strictly real, the operator is perfectly Hermitian, and the trace formula is perfectly mass-balanced. Now look at the flaw on the right. The absolute second S doesn't equal 1/2. The eigenvalue picks up an imaginary component. The global operator instantly becomes non-Hermitian, and the unitary dualities of the trace formula are completely shattered. It forces a massive mathematical contradiction.
But honestly, it's so much worse than just a mathematical contradiction. The real part of the zero governs the amplitude envelope of the vacuum energy wave. Notice the waves on the slide. At precisely 1/2, the wave is pure, undamped, and perfectly conserved. But a stray zero creates an asymmetric amplitude envelope. It becomes either an uncompensated energy surge or a dissipating vacuum sink. A non-Hermitian operator physically tears the Gilles-Salé effective metric, which means a stray zero literally causes an immediate collapse of the spacetime continuum.
And that brings us to our final mathematical proof. The stable existence of the macroscopic physical laws we experience every single day is, in itself, the proof that the vacuum energies are perfectly balanced. The GUE level repulsion we filtered out earlier acts as that cosmic thermostat. It ensures the zeros are locked, uniformly spaced, and permanently anchored to the critical line. The critical line is the unbreakable anchor of the vacuum. We've built the operator, we've traced the spectrum, and we've stabilized the vacuum. The fact that you inhabit a stable universe right now is the ultimate proof of the Riemann hypothesis. It really leaves you wondering, what other cosmic blueprints are hidden in pure mathematics, just waiting to be uncovered? Thanks for joining me on this deep dive, and I'll catch you next time.